Hello everyone, today we'll be trying to see what an inertial force is and we'll be trying to legitimize the use of centrifugal force. So let's get started. At first what we'll do is consider the motion of two particles in an inertial frame. We'll call the inertial frame to be S. So this is our inertial frame S. And these objects, we will denote their masses by m0 and m1. You can call them as the first object 1, object 0 or whatever. Object 1. This is object 0. Okay, so these objects have their own radius vectors or position vectors like that. These are something like this. So this is, I'll call this r0 and this will be r1. So these masses will have different kinds of acceleration. Let's say this is the acceleration a1 and this has the acceleration of not parallel, something like this. Let's say these accelerations are arbitrary. We don't need them to be fixed in any direction whatsoever, neither in magnitude nor in direction. So this is a0. Now what we will try to see is the relative position of m1 with respect to m0, or we will be trying to measure, or I mean not measure, but observe the position of object 1 with respect to object 0. So the measurement we'll get is this vector, and this is the relative position of object 1 with respect to object 0. From the law of vector addition, we can see that r1 is equal to r0 plus r10, which is the relative position of object 1 with respect to object 0. So what we are trying to see is the r10, which can be written as r1 minus r0. So we will pick this up right now and we will differentiate it one time to get with respect to time, I mean. So if you differentiate it with respect to time, you will get the relative velocity. So v of 10, which is the relative velocity of object 1 with respect to object 0, is equal to r1. So we will get the velocity of 1, object 1 I mean, minus velocity of object 0. We will differentiate it again with respect to time. We will get a10 is equal to a1 minus a0. Now what we've got in here is this equation. So I'll try to read over what I've gotten until now. This is acceleration of object 1 with respect to object 0, and this is the acceleration of object 1 with respect to inertial frame S, and this third one is similar, which is the acceleration of object 0 with respect to S, and these two are with respect to inertial frames, right? Inertial frame. Only this is with respect to object 0, which is non-inertial frame, which is a non-inertial frame. Right? As this is non-inertial, we have already established an equation which relates accelerations from inertial frame to accelerations in non-inertial frame, and our non-inertial frame lies with the motion of this object, right? So object 0, you can consider the frame, the non-inertial frame, to be this objects, like you can consider the origin of the non-inertial frame to be the position of this object itself. So it's completely fine, and the vector representation doesn't really matter, so you can orient it at any way possible. Actually, it doesn't really matter. What we are going to do now is multiply this with m1. So we will get m1 a10 is equal to m1 a1 minus m1 a0. Done. So what is this? This is the force which is observed by object 0 on object 1. So this is not a force that's measured from an inertial frame. This is a force, net force, which is measured by an object which is moving in some certain acceleration, which means that we are measuring this force in non-inertial frame, which is equal to m1 a1. So this is the force on object 1 in inertial frame, because the acceleration a1 is the acceleration of object 1 in the inertial frame. So the final part, m1, and this minus will come here, so it will be minus a naught vector. Okay, so we have found a new rule, and we will be trying to see what this really means. Okay, so this part, this is the force observed by object 0 on object 1, or this is the force observed that's being acted on object 1, but this is with respect to object 0, which is itself non-inertial frame. Okay, this is the, this was the net force, of course, net force, and this is also the net force, but this is net force on object 1, but this is with respect to an inertial frame, which is S, and its inertial frame. Okay, so this last one, this is the extra term, and we call this inertial force, also called fictitious force, also called pseudo force. So as we have gotten this far, now what can we really do? We can use this. It is actually the same equation as the second law, but it has a correction term. This is the correction term which is needed when you are in non-inertial frame. This is needed if and only if you are in a non-inertial frame. Okay, so, and we have derived it from really like from the basics of position vectors and the relative position. We have derived it from there, so there is nothing wrong with it. Okay, so what's the use? We can use this to legitimize our use of centrifugal force, and you may have already guessed how this works, right? Our example will be, our only example right now here will be the uniform circular motion. Okay, we are going to consider an object that has the speed v, tangential speed of force, and the speed does not change. Okay, the speed does not change, so it is a uniform circular motion. Okay, so I have already shown you in another video that when you are moving in a circular path with a fixed velocity, you need a force to the center, or directing toward the center, which is the magnitude m v squared divided by r, where r is the radius of the trajectory and m is the mass of the object. So the acceleration we need towards the center is the centripetal acceleration AC is equal to v squared divided by r. Okay, so what we're going to do now is move it aside. So for our analysis, we can consider this to be a car. Maybe this should be something like this. So for our car, the acceleration, if the speed is v and the radius is r, then the acceleration that's required for it to go around the circular path is v squared divided by r, and it should act in the radially inward direction. Okay, so that's what we already proved. Okay, now if we are trying to see it in a non-inertial frame of sense or whatever, if we are trying to see this car in a different manner, let's say there is a mass of m naught, okay, mass of m naught, which is on top of this car, okay, but does not interact with this car, so no interaction. Okay, no interaction, but this is on top of the car at every moment. Okay, if this thing is on top of the car every moment, then the movement of this object can be described by something like this. I think I'll copy it, paste, and if this is m naught, of course this was, if this is m naught, then m naught, then its motion is the same as this one. Okay, so the acceleration has to be radially inward, and which has to be equal to v squared divided by r. So as we've already seen, if we are trying to see this from the perspective of m naught, or the object 0, Okay, so this is the non-inertial frame we are talking about. Okay, or the rotating frame. So if it's the rotating frame, then what we need is not the a naught, we need minus a naught. So minus a naught. Okay, so from here, what can we really see? We can see that at every moment of time, this object m naught or object 0, it always stays on top of this mass, right? It always stays on top of this mass. So with respect to m naught, this car is stationary. That means its acceleration must be 0 with respect to m naught. So with respect to the non-inertial frame, the force is itself is 0. So F10 is equal to F1 plus M1. I mean the M1 is this one, so this is M1, this is M1, this should be boxes. So M1 minus A naught. Okay, so from the perspective of object 0, this is 0, right? The force on object 1 is 0 because it's stationary with respect to the M naught, okay, on the object 0. This is equal to 0. If this is equal to 0, this is an equilibrium condition, right? So with respect to object O 0, whatever, the car is in equilibrium, right? The car is in equilibrium with respect to m naught or object 0. So you can apply equilibrium condition on this. Okay, so from that what you really get is F1 is equal to, just put it here, so and change the sign of course, so M1 A naught. And you already know this one, right? You already know this one, you must. Okay, this acceleration is the same as radially inward acceleration that this one needs. Okay, these two follow the same radial trajectory, so of course they need the same acceleration, and therefore this is what we know as the required force, which is required force for M1, right? This is the required force for M1. And see, this equation comes from the equilibrium condition. Okay, this equation comes from the equilibrium condition. This equation, what it really means, like this. So this is the object, I mean car, and there is a force F1. Of course, it is going a circular path. Its velocity is v, and this is F1. Okay, and it must be neutralized by this force, which is M1 minus A naught. As we have already seen that the direction of minus A naught is radially outward, and of course as F1 has to balance this one out, so of course it is in the opposite direction. It's radially inward. So that's about it.
Bye everyone. Thank you for watching. See you later.